NASA's got a dirty secret. Their moon landing hinges on something that's never been done. Refueling Starship in orbit. 12 tanker launches, 12 chances for catastrophe. One delay, one docking failure, and billions vanish. SpaceX knows it. NASA knows it. Then Elon's team leaks something wild. Nuclear-powered Starship. No refueling. Round-trip capable. Cuts risk by 75%. Sounds perfect, right? Except there's a reason nobody's done it. Radiation, regulations. And if it fails? Chernobyl in orbit. Let's dive right in. Here's what NASA doesn't mention in their polished Artemis videos. Their entire moon landing plan is built on something that's never been proven at scale. Orbital refueling. And not just once. 12 separate times. 12 tanker launches. 12 precision dockings at 17,500 miles per hour. 12 fuel transfers in the freezing vacuum of space. Each launch runs about $100 million. Each docking is a high-stakes operation where hundreds of tons of super-cold propellant must flow between vehicles without a single leak or valve failure. The brutal math? Even if each step has a 98% success rate, optimistic by the way, stacking 12 operations drops your odds to roughly 78%. That's a 1 in 4 chance of mission failure before astronauts even leave Earth's orbit. But the real killer is time. Liquid oxygen and methane don't just sit quietly in space. They boil off constantly. NASA estimates the orbital fuel depot remains viable for only a few weeks before too much propellant evaporates. So you're racing against the clock. Launch 12 tankers in rapid succession, dock them all perfectly, then get the crew vehicle and lunar lander up there before your fuel turns to vapor. One weather delay, one technical glitch, one tanker failure. The entire timeline collapses and billions of dollars evaporate along with the propellant. This isn't speculation. This is NASA's current architecture. And it's exactly why SpaceX has been quietly exploring something radically different. What if you could skip the refueling circus entirely? What if Starship could fly to the moon, land, and return home without needing a single tanker launch? Nuclear thermal propulsion makes this possible. And before you picture Chernobyl in orbit, understand this. The technology is real, the engineering is solid, and the performance numbers are staggering. Here's the breakthrough. Instead of chemically burning methane with oxygen, a nuclear reactor superheats the methane to extreme temperatures and expels it at tremendous velocity. The result is a specific impulse of 625 seconds, nearly double what chemical rockets achieve. Translation: you get twice the efficiency from the same amount of fuel. The numbers tell the story. 3 nuclear engines producing a combined 7,828 kilonewtons of thrust. Total mass, including radiation shielding, 24 tons. Load up the standard 617-ton methane tank, and you're looking at 7,290 meters per second of delta V from Starship alone. Combined with the 3,944 meters per second from Super Heavy's launch boost, you hit 11,153 meters per second total velocity change. Compare that to chemical Starship, which barely scrapes together enough delta V for a one-way moon trip with payload. The nuclear variant? It carries 25 tons to the lunar surface and brings itself back to Earth orbit, fully reusable. 0 refueling required. The mission architecture becomes dramatically simpler. Instead of 12 high-risk tanker flights, you'd need maybe 3 launches to top off the nuclear Starship in low Earth orbit. The complexity drops by 75%. So does the risk. In maximum payload configuration, nuclear Starship could deliver 271 tons to the moon one way, nearly triple the chemical version's capacity. You could land entire habitat modules, power systems, and years' worth of supplies in a single mission. This is exactly what NASA needs for sustainable lunar presence, which makes the next part even more frustrating. The technology exists. The math works. So what's stopping SpaceX from building a nuclear Starship tomorrow? Reality. And it comes in 3 brutal forms. First, access to nuclear technology requires government authorization that SpaceX simply doesn't have. The enriched uranium needed for these engines is weapons-grade material under strict federal control. We're talking Department of Energy oversight, Nuclear Regulatory Commission approval, and years of security clearances. This isn't something a private company can develop independently, no matter how much Elon Musk tweets about it. Second, SpaceX's entire success formula breaks down with nuclear systems. The company dominates the launch industry through rapid iteration: build, test, explode, learn, repeat. They've destroyed more prototypes than most nations have launched, and that aggressive testing cycle is exactly why they innovate faster than anyone else. You cannot iterate like that with nuclear reactors. If a nuclear-equipped Starship explodes at Starbase, it's not another rapid, unscheduled disassembly that gets memed online. It's a federal emergency. Radioactive contamination, evacuation zones, EPA, NRC, and DOE investigators swarming the site. Congressional hearings, potential criminal liability. The move fast and break things philosophy dies the moment nuclear material enters the equation. Every test becomes a multi-month approval process. Every failure triggers exhaustive investigations. SpaceX's competitive advantage, speed, vanishes completely. Third, the radiation problem is more complex than most people realize. Here's what's surprising. Before ignition, these engines are relatively safe. Low-enriched uranium fuel in solid form isn't dangerously radioactive. Launch crews could work around an inactive nuclear Starship without hazardous exposure. Even if a launch vehicle carrying a dormant nuclear engine exploded on the pad, you wouldn't get a Chernobyl-style disaster, just contamination requiring cleanup, not mass casualties. The danger starts when you fire up the reactor. Once active, the fuel becomes intensely radioactive and stays that way for weeks. Even after shutdown, the reactor continues outputting up to 1% of maximum power, several megawatts of residual heat and radiation. NASA's analysis shows it takes roughly 1 month after operation before a nuclear engine is safe for humans to approach. Now imagine this scenario. Nuclear Starship completes its moon mission and lands back on Earth using its chemical Raptor engines. Perfect landing. Except now you've got a vehicle sitting on the pad with a nuclear engine still radiating lethal doses of energy. How do you refuel it for the next flight? How do you load cargo? How do you perform routine inspections? Ground crews need radiation suits and specialized equipment, remote handling robots, heavy shielding infrastructure. SpaceX dreams of 24-hour turnarounds between flights. With nuclear propulsion, you're looking at weeks minimum, possibly months. This completely undermines the business case for reusability, which is the entire point of Starship. Even if SpaceX solves the regulatory and operational challenges, there's still the engineering puzzle of protecting astronauts from their own propulsion system. Starship's current design, that sleek cylinder with large control flaps, wasn't built with nuclear engines in mind. Those flaps work beautifully for atmospheric re-entry, but they create a dangerous side effect. During nuclear engine burns, radiation reflects off the flap surfaces and scatters back toward the crew compartment at the top of the vehicle. The fix seems simple: retract the flaps during burns. But that's just the beginning. You also need shadow shielding, specialized layers of materials like tungsten, lithium hydride, and boron composites positioned close to the reactor. These materials absorb different radiation types and create a protective shadow zone where humans can survive. The problem? Mass. Every kilogram of shielding reduces payload capacity. The engineering becomes a ruthless optimization. How much protection is genuinely necessary without making the vehicle too heavy to fulfill its mission? And here's the question that keeps safety engineers awake. What happens when things go wrong mid-flight? Chemical engines shut down instantly. Nuclear reactors don't. That reactor keeps generating heat and radiation for weeks regardless of circumstances. If a nuclear Starship suffers a critical failure halfway to the moon, the crew is trapped with an active reactor that can't be turned off. What's the emergency protocol for that scenario? NASA hasn't published one because we've never needed one. That should tell you something about how far this technology still is from human-rated flight status. This is where the story takes an interesting turn. NASA Administrator Sean Duffy recently announced plans to deploy a nuclear fission reactor on the lunar surface by 2030, not for propulsion, But for power generation, why nuclear? Because Artemis isn't just about planting flags. The long-term vision involves extracting lunar resources, water ice from permanently shadowed craters, oxygen and hydrogen for spacecraft refueling, raw materials for construction. The goal is reducing Earth launches and establishing true self-sufficiency. But industrial-scale resource extraction requires serious power. Megawatts running 24/7 through the 2-week lunar night when solar panels are useless. That means nuclear reactors. No other option delivers that combination of power density and reliability. Here's where it gets strategically interesting. NASA is already committing to nuclear infrastructure on the moon. The regulatory frameworks, safety protocols, and operational procedures must be developed regardless, which raises an obvious question. If we're going nuclear for the moon base anyway, why not for the transportation system too? Perhaps nuclear Starship isn't meant to replace the current Artemis architecture. Perhaps it's designed to enable the next phase: permanent settlement, industrial operations, the true colonization of the moon. The 12-tanker refueling approach represents a minimum viable solution. Get boots on lunar soil fast enough to meet political deadlines with existing technology. It's not elegant or efficient, but it might be the only path to achieving Artemis 3's 2027 target. Nuclear propulsion is the long game. It's what you develop after proving you can land humans on the moon and return them safely. Once political pressure eases and the focus shifts from deadlines to sustainability and cost-effectiveness over decades of operations. Let's address the elephant in the room. Timing. Developing, testing, and certifying a nuclear propulsion system for human spaceflight would require at least a decade under normal circumstances. NASA studied nuclear thermal rockets extensively during the 1960s and 70s. We still don't have flight-ready hardware. SpaceX moves faster than traditional aerospace? Absolutely. But even with unlimited funding and regulatory fast-tracking, you're looking at minimum 5 to 7 years. And that assumes everything proceeds smoothly, which never happens with revolutionary technology. Meanwhile, Artemis 3 launches in 2027, Artemis 4 in 2028. Tanker Starships are already under construction. Refueling demonstrations are scheduled for 2025 to 2026. The imperfect current plan exists in hardware form right now. Nuclear Starship remains a concept study with impressive PowerPoint slides. So why surface these nuclear propulsion details now? Strategic positioning. SpaceX is signaling to NASA, if orbital refueling proves too risky or problematic, we have a technically superior backup plan. It takes longer and costs more upfront, but delivers better performance and sustainability long-term. It's also potentially a negotiating move. SpaceX's Starship HLS contract is worth billions, but demands unprecedented capabilities. Demonstrating that nuclear propulsion is feasible might justify expanded contracts, additional funding, extended timelines, and position SpaceX as the inevitable choice for next-generation lunar infrastructure. Because here's the real prize. Whoever controls transportation to the moon controls humanity's expansion into deep space. That's not just a NASA contract. That's the foundation of a multi-trillion-dollar economy waiting to be built beyond Earth. And SpaceX is making sure they're the only company with cards to play at that table. Here's the bottom line. NASA's refueling plan isn't a failure waiting to happen. It's the necessary first step. Chemical Starship gets astronauts to the moon by 2027. Nuclear propulsion keeps us there permanently. 2 different strategies, 2 different timelines, both essential. This is exactly why SpaceX revealed these nuclear specs now. They're not replacing the current plan. They're showing NASA what comes next. Because once orbital refueling proves viable, even imperfectly, nuclear becomes the obvious evolution. The question isn't if, it's when. And here's the piece most people are missing. That 2030 lunar reactor isn't just about powering a moon base. It's the proving ground. Demonstrate nuclear works safely on the surface, and suddenly public and political acceptance for nuclear spacecraft becomes realistic. Everything starts there. What we're witnessing is the blueprint for permanent human presence beyond Earth being written in real time. Chemical propulsion opens the door. Nuclear propulsion lets us stay. What's your call? Should NASA accelerate the nuclear timeline despite the risks, or master refueling first then go nuclear? Let me know in the comments. This is Space Hub, where we cut through the hype and show you what's really happening in space exploration. If you want more deep dives like this, hit that subscribe button and turn on notifications so you don't miss what's coming next. Because the moon race? That's just the warm-up. The real game is building civilization beyond Earth, and it starts now.